We're going to take a look and see how we can use Excel to expedite our computations for these Euler's methods for second order differential equations. You might remember in the previous video that we had this differential, y double prime plus xy prime plus y is equal to 0. And we had the initial condition that y at 0 was equal to 1. We had y prime at 0 is equal to 2. And we had our step size h was 0.1. All right. Now recall that we used a substitution. Okay, so remember that u is equal to y prime. So another way to write u, or y prime at 0, is we could say that u at 0 is going to be equal to 2. We know, and this is just our initial value, so we could actually just say u sub 0 is equal to 2. We know that y0, which is the first y, is equal to 1. We know that x0, the first x, is 0. And we know, of course, the step size h is equal to 0.1. All right, that's just given above. The other thing that we need is we need to solve for the second derivative. So a couple ways we can write this. Y double prime equals negative xy prime minus y. Another way to say this is that u prime is going to be equal to negative xy prime minus y. But probably the preferred way we'd like to write this is that the function at x comma y prime is going to be equal to minus x y prime minus y. And by the way, these are all the same thing. It's just different ways of denoting them, and I just want to make sure everybody's okay with the different denotations. Or probably the most useful way we can write this is f at x comma y comma u is going to be equal to minus xu minus y. All right, our formulas. Remember that yn plus 1 is equal to the current y plus the step size times u of n, or u sub n. And then the next u is going to be equal to the current u, so the current slope, plus the step size times the slope of the slope. And that's going to be the function x comma y prime, or just f comma y comma u. All right, so let's go ahead and program this. So we know our first x is 0, and then from there the step size is 0.1. The goal is to be able to get to 0.5. All right, so we just stop there, and we have 0, 1, 2, 3, 4, 5 for our iterations. Our first y is 1, and our first u is 2. So we have to hard code these. Now, what is the next y value, or in other words, the y approximate value? Well, we're just going to use our formula. All right, so this formula right here says that it's going to be equal to the current y plus the step size times the current u. And remember, we got 1.2. It's 1.2, not surprising. The next u is going to be equal to the current u plus 0.1 times f at x comma y comma u. So that's where we're going to use this formula right here, the negative x u y. So it's going to be minus 1 times x, which in this case is 0, times u, which in this case is now 2, and then minus y, which is 1. And you might remember that we got 1.9 for this. Well, it's 1.9. Right? Now that we've programmed it, the next x, or the next y, excuse me, is just going to be this column, and the next u is going to be equal to what's right here in the next u column. Right? And then now we're going to just drag these down. Now it's going to look like a bunch of mumbo jumbo initially because it's recursive. All right, and then here's the telling part to see if it works. All right. Now you might remember when we did this by hand, y1 was equal to 1.2. u1 was equal to 1.9. y2 was equal to 1.39. And again, we did this by hand in the previous video. And then u2 is equal to 1.761. And I want you to notice that 1.9 and 1.2 are u and y respectively. And then 1.39 and 1.761 are y2 and u2 respectively as well. Generally, if you do it by hand, you get the first two iterations, and you do it by computer, and you get the first two iterations to be the same. Usually your algorithms are correct, and that's why we have both of them. So my suggestion to you would be maybe do one or two of the iterations by hand, and then to go through and use the computer, especially Excel because it's so easy to use, and just try to determine whether those are correct or not. All right, so let's determine how accurate we are. All right, and remember we were pretty accurate with the first iteration, so let's see what happens with this. All right, let's go through and find y actual and u actual. All right, so you might remember that we had the series solution. All right, so all I'm going to do is just plug in 0.1, all right, into our y actual, or 0 in this case. So that's going to be 1 plus 2 times 0 minus 1/2 times 0 squared, or that cell squared, minus 2/3 times this cell cubed. And again, this is the series solution that was given to us. All right, so check your guided notes. You can see that somebody produced what the series solution was for that. Right, plus 1/8 times this cell to the 4th power minus plus 2/15. That would be bad if I put a minus in there. Plus 2/15 times this cell to the 5th power minus 1/48 of this cell to the 6th power, and then finally minus 2/105 times this cell, which is B2. It looks like I might have run out of room. B2 to the 7th power. All right, and the y actual is 1, which makes sense because that's the initial condition. All right, now let's drag this down, and that's going to be our y actual. And you might remember that we ended up with 1.194347, and I plugged that in before. This is actually how I did it. All right, let's find the error. All right, and you'll notice that the y actual and the yn, the predicted, are pretty close to one another for each of these. Let's find the error. All right, so the error is going to be the approximate minus the actual divided by the actual. And of course the first one's 0 because it's the initial condition. And notice that we get a pretty good error here, okay, about 3.3%. So it's pretty reliable for us, especially considering that we didn't do a lot of work to find a series solution. All right, the approximation just did it for us. Now let's program the u actual, and that's where we found the derivative of the series. All right, so let's just go ahead and do that first. So we found the derivative of our series, so that's 2 plus, or 2 minus, that's going to be x, which in this case is 0, minus, that'll be 2x squared, so 2 times this cell squared, plus 1/2 times the cell cubed, plus 2/3 times the cell to the 4th power, minus 1/8 of the cell raised to the 5th power, and minus 2/15 times the cell to the 6th power. All right, and the u actual should be 2, which is not surprising. Here's the approximations for u prime, or the actual values for u prime, using a 7th degree polynomial. And then let's find the error. So that's going to be the approximate minus the actual for u divided by the actual. All right, first error is 0, not surprising. And our errors, the most error we get is about 5.15%. So this is a pretty reliable algorithm considering how big our step size is. All right, and you might not think that 0.1 is a big step size, but it actually is. Now let's see how good the algorithm is if I was to reduce the step size. All right, so let's just make the step size 0.01. All right, now this is all going to change, and we're going to need a number of iterations. All right, because remember we're looking for 0.5. All right, so we're going to have to go all the way down to this column 52. Not a big deal. All right, and Now before we do anything, we have to change the step sizes. All right, so let's go up here. The only two cells that are affected by the step sizes are right here, next Y, next U. It's a pretty simplistic algorithm. So now we're going to do 0.01, and we're going to have 0.01 right here. All right, now let's drag everything. All right, so I'm just going to drag all of it, and let's see what happens. Alright, so there we go. Alright. Let me check again just to make sure I didn't do anything wrong, because it looks like the error actually got kind of big here. Let me undo this. So I might have to drag all of this down individually. So, and let me make sure that there's no other functions being affected by the step size. I did plug in the step size, it looks like correctly. So let's just drag these down individually. Alright, and again, until we drag everything down, it's going to look a little bit weird. Alright, but that's okay. Oh, I see what I might have done. I know. I think this first one was just 1, so I actually have to start here and drag it. Alright, so I'm going to drag this. Alright, so that's why I think I suggested that you drag one at a time, just because it's recursive. I'm going to start here and drag. Alright, so just bear with me as I do this. It shouldn't take us too long. Or you can just fast forward if you want, or you can just watch as I drag it all. Alright, so we're getting here. This is pretty cool that the first error is really small. Alright, so let's see if when we're done we end up with a pretty decent error as we go along. It's probably not going to be too decent initially, but as we move along it'll probably get a little bit better. Alright. Alright, and then alright, now be careful. If you start here and drag, notice that you have 0.1 as your step size, so you actually have to start above that. So just be careful if, when you're doing this. I did that a couple of times when I was practicing these. Alright, and then finally, this guy right here. Alright, and notice that this time our error, right, so this is our Y error. Our Y error is 0.3%. I think last time it was 3% or something like that. And then notice the slope error is about 0.5%. So if I wanted to change these into percentages just to see, you know, what type of percentage we get. So I'll format this cell, I'll make it into a percentage. Alright, so yeah, we get a really good approximation this time. And again, we just changed the step size. Let me change this one just to show you what's going to happen. So we're going to format the cell. We're going to change it to a percentage. And I'll bump that up to 6 decimal places. Notice the percentage is very small. We're less than 1% error. And of course, very easily we could just make the step size 0.0001 if we wanted to, and make the approximation even better. Again, the whole purpose of this is because maybe we don't want to find a series solution to a differential equation. Maybe we just need what the value is at that point, and we don't want to go through and solve the method of Frobenius, or we don't want to go through and solve the ordinary methods. So this is a really cool way, using a very low-powered algorithm, to be able to approximate the solutions to these second-order differentials. So pretty cool to me. Hopefully when you guys go through and do this, this is helpful for you to be able to see how to go through and program using Excel.